There are often guidelines behind the type of counting that we want to do, and here is one of them. Suppose you want to count the number of ways that R items can be chosen from n of them. Okay, where R is less than or equal to n. So in other words, I have n total objects, and I want to select R of them. Well, the most that I could select is all of them. I can't select more than there are items. I can't select more than n, but I could select as few as 0 and as many as n. So this is our little stipulation on that. And also, let's say the following two principles apply. First of all, items that have already been selected cannot be selected again. So I like to think about the idea of if I'm going fishing in a pond, and I have a few different fish here, I'll use my artistry, and if I catch one of those fish and I take it home, that fish is no longer available to be caught again. And also, if the order in which those items are selected is important, okay, so if the order in which I select the fish becomes important, then each outcome is called a permutation. The number of outcomes is called the number of permutations. So here's an example. Consider the word cat, C-A-T. How many words can be formed from these three letters? Well, assume that those words don't have to be meaningful, but how many ways, in other words, can I rearrange these letters in? Okay, well, of course I have C-A-T. I can do C-T-A, just rearranging those last two letters. I could have C in the middle position, and then I could have T-A in the first and the last. I could have C in the middle position, A in the first, T in the last. Oh, there's a word, act. And then I could also have C in that last position. I could have T-A-C, or I could have C in the last position, have A-T-C. So we could list them all out. There are 6 possibilities. Another way we could think about this is the first letter, L1, L2, and L3. And I could draw a tree diagram and say, well, the first letter could be one of 3 possibilities. It could be C, it could be A, or it could be T. Okay, now notice that this does satisfy our criteria. We can't select the same letter twice. We're just asking for the number of ways that we can rearrange these 3 letters. And also the order is important, right? Because each of these 6 sequences forms a different word, so to speak. So in branch 2, the difference here is that if C was selected as the first letter, then there's only 2 letters left for that second letter. There's A or T. If A was the first letter, then only C or T are left to be selected. And if T was selected first, then I can make letter 2 a C or an A. Now, if I had C and A as the first letter, then that only leaves 1 letter remaining. There's specifically T available. If C was the first letter, T was the second letter, then only A is available for the third. A, C, T, A, T, C, T, C, A, or T-A-C. Right? So every branch omits one of the possibilities from the previous branch. And if you look at this for a moment, you're like, okay, well, I see that there are 6 different possibilities. How could I do this without listing them all out? Well, we can think about this another way, and we can say, let these 3 lines represent the number of possibilities at each letter. So here's letter 1, here's letter 2, here's letter 3. There are 3 possibilities for the first letter. And each of those 3 possibilities, notice, has 2 branches coming off of it to form a pairing with the second letter. So there are only 2 possibilities. Each of those 3 letters can be paired with only 2 other letters. So you notice there are already 1, 2, 3, 4, 5, 6 possibilities at that third letter. And now for letter 3, because 2 of them are already gone, they're 2 fish have been pulled out of the pond, we only have 1 possible letter for the third letter. And so this gives us 6 words, and I won't put the quotes on that, but 6 different words that we can form. So we have sort of, hey, let's list them all out approach. We have, let's come up with something a little bit more formal so that we don't miss any arrangements. And then let's do it without listing any arrangements at all. And of course, this approach is probably the best. I think sometimes it's helpful to begin a tree diagram to help us visualize things a little bit and to find a pattern and then move on to this. But sometimes it's just necessary to start with the counting approach. So there are 6 words. We call these 6 permutations because, once again, we had n items. So we have n equals 3 items. We're selecting r equals 3 of them. So notice that we're choosing all 3 of those letters. And again, that stipulation of r is less than or equal to n applies here because we can select that most as many as we have. Let's look at another possibility. What if we took the word cats? So now there's 4 letters in that word, but the question is how many 3-letter words can be formed from this word? Again, assume that they don't have to be meaningful. Well, again, we can start listing them out. We'd have definitely these 6 possibilities because we don't have to use S, we just have to use 3 letters. But then now we have to look at all the possible words that we can form with one of them being an S. And we're not going to go ahead and begin listing them out, but you can kind of imagine the only difference here is for letter 1, there are now 4 possibilities. C, A, T, or S. But if C was selected as the first letter, now there are only 3 possibilities, namely A, T, and S. And by the way, the number of branches extending out of A, T, and S will also be 3, except that the 3 branches on the letter 2 column will be C, T, and S as possibilities since A has already been selected. And remember how I said in example 1, sometimes we just start off by listing a tree diagram to get a visualization, and then we let something like this do the computation for us. So if C and A were selected for the first 2 letters, then only T and S are available for that 3rd letter. So notice that we have 4 possibilities here. Then for each of those first letter selections, there are only 3 possibilities in the second table. That'll be the same thing for this guy, for this guy, and for this guy. And then depending on what the second letter was that was selected, there are now only 2 possibilities. So I've just kind of started listing this tree diagram to get the visual that gives me everything that I need in order to know how to use a multiplication principle to come up with the number of possibilities. So there's 4 for the first letter. Each can be paired with 3 possibilities for the second letter, each of which can be paired with 2 possibilities for the 3rd letter. 4 times 3 times 2 is 24. So there are 24 permutations where n is 4. We have 4 letters. We're only going to pick 3 of them. So here's a more interesting problem. Of course, we're not often interested in looking for rearrangements of letters, but again, it illustrates the idea of counting. So let's just put this instead of letters. Let's say that we have 8 candidates. And instead of selecting 3 letters from 8 letters, let's say we're going to try to fill 3 different board member roles: president, vice president, and treasurer. So we have a pool of 8 people. From them, we want to select 3 of those people. And our criteria is again satisfied because we can't have one board member or 2 different positions be filled by one board member. So it just doesn't work that way. We can't have Jane be president and vice president, and we certainly can't have one person take on 3 different roles. So yes, certainly, items that have already been selected, so people that have been chosen, cannot be selected for another position. And the order in which they're selected is important. Well, why is that in this case? Well, it's because they're three different roles. So having the sequence of Jane, Dave, and Sue, Jane being president, Dave being vice president, and Sue being treasurer, is different than Sue being president, Jane being vice president, and Dave being treasurer. So the arrangement, the order in which these three people are selected does matter. So let me again start off with a tree diagram here. I have three different board member roles: president, vice president, and treasurer. So I'll start the root of my tree. So who do I have available for president? Well, any one of the 8 candidates, right? Candidate 1, candidate 2, all the way down to candidate 8. So notice how I'm just beginning to map this out so I can see what's going on here. I see that there are 8 possible ways I could fill the president role. But then for the vice president role, if candidate 1 is selected for president, now only candidates 2 through 8 are available to fill the vice president role. So you see we've lost one candidate because that person is in the president role. There are only 7 ways we can fill the VP role. That's the same thing for if candidate 2 were the president. Now vice president could only be 1, candidate 3, candidate 4, all the way up to candidate 8. So there's still 7 different people that can be selected. And then for treasurer, you can imagine now that if candidate 1 is president, candidate 2 is vice president, then the treasurer can only be one of candidates 3 through 8. And again, this top rung of the tree just helps me get enough of a sense to see that I'm counting permutations here. In my case, there are 8 people that could fill the president role, 7 people left to fill the vice president role, 6 people left to fill the treasurer role. 8 times 7 is 56. 56 times 6 is 336 permutations. Okay, in this case, the permutations represents the number of boards that can be formed. So there's a lot of different ways that those 3 seats can be filled. There are 336 of them. And remember, that includes the same 3 people multiple times, except in just different rearrangements of those positions. So president could be, like we said, Sue, vice president, Dave, treasurer, Jane, or Jane, Dave, Sue, or Jane, Sue, Dave. And there are a number of ways that we can rearrange those 3 people. But they're all important because we're assuming that the first person listed is the president, then the vice president, then the treasurer. So you can see these quantities can start getting fairly large, and there are lots of different types of questions we might want to answer with them. What if there are too many quantities to multiply? Like, let's say instead of having 8 candidates, I had 100 candidates, and I'm filling 50 board member roles. Well, you can imagine that's going to require 50 multiplications, and that's just too many to try to do by hand. So let's define something first. This quantity, by the way, is called the, we're going to call this the factorial of n. And no, this isn't just a really loud n. This actually means n factorial. N factorial. It's just a notation that we use as a shorthand for when we're multiplying from that non-negative integer all the way down to 1. So n times n minus 1 times n minus 2, dot, 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 all the way to when we get to 1. So as an example, 3 factorial is 3 times 2 times 1, which is 6. 5 factorial would be 5 times 4 times 3 times 2 times 1. 1 factorial would just be 1 because, well, that's already down to the lowest point. Now there is one issue that we'll encounter, and that is, well, what about 0? Well, because 0 is technically non-negative. So we actually have a definition for 0 factorial, and you might say, well, would that just be 0 times 1? And no, we're going to just say, by definition, let 0 factorial be equal to 1. Because otherwise 0 kind of breaks the system a little bit. So this is just a definition. And there is some logic to this. For example, let's say that I have 8 candidates and I'm going to select 0 of them. Well, how many ways are there to select 0 candidates? You might say 0 ways, but there's actually one way to do it. And that is by not selecting anybody. Okay, so it has some intuitive meaning behind it. All right, so we can obviously use this in some of what we've encountered already. At least in example 1, we had 3 times 2 times 1. We had 3 times 2 times 1, which we could write as 3 factorial. Now let me write something here that might seem like it's obvious, but you'd probably agree that 3 times 2 times 1 is equal to 3 times 2 times 1 divided by 1. Okay, nothing fancy going on there, but it still is the same thing. And you might also notice that this is 3 factorial divided by 1 factorial. Okay, why am I writing it like that? Well, in a moment you'll see. Because in example 2, our multiplication was 4 times 3 times 2. Well, that's really the same thing as 4 times 3 times 2 times 1 divided by 1, which is once again 4 factorial over 1 factorial. Still, not very interesting. But look at example 3, where our multiplications don't go all the way down to 1. It's 8 times 7 times 6. But I'm going to write 8 times 7 times 6 like this. I'm going to say this equals 8 times 7 times 6 times... Okay, wait a minute, what do you mean times? There's nothing left there. Well, I'm going to write in 5 times 4 times 3 times 2 times 1. You're like, well, but you just changed the problem. And the only way to not change the problem is to also divide by 5 times 4 times 3 times 2 times 1. Because you agree that these cancel out in the numerator and denominator. But the advantage that I get here is that by writing it like this, I can express it as 8 factorial divided by 5 factorial. Okay, why would we want to write it like that? Well, because it's easier to plug that into a calculator than it is to necessarily have a bunch of multiplications, especially if we had, as I mentioned earlier, 100 candidates and we have 50 roles. We would have to do 100 times 99 times 98 times 97 all the way down to actually 51, because we're starting at 100 and then counting down from there. But I want you to notice that 8 is the total number of candidates that we had. This was n. That's how many people we had to choose from. And the reason we took 8 times 7 times 6 was because there were 8 candidates that could fill the first position, but only 7 to fill the second, 6 to fill the third. But what's the connection to this 5? Well, the 5 factorial was actually all the terms that I was missing. It was all of this right here. And really that, the fact that I only had 3 quantities to multiply together here was because there were only r equals 3 positions, right, that I wanted to fill. So if I have 3 positions to fill, but I have n equals 8 candidates, then notice that 8 minus 3 will tell me how many extra factors that I actually don't have in the numerator that I need to divide out if I'm going to write 8 factorial in the top. So this 5 is actually the quantity n minus r. Okay, so what I'm claiming is that the easiest way that we could actually calculate the number of permutations is by taking n factorial divided by n minus r factorial. Now factorials don't distribute. You have to do this first and then find whatever that factorial is. Some people want to say, well, can I distribute and make this n factorial minus r factorial? It doesn't work. You can try it and see that 8 minus 5 or 8 minus 3 factorial is not the same thing as 8 factorial minus 3 factorial by a long shot. Would that same thing apply up here? Well, up here, I actually have, well, 4 was n. I had four letters. And n was equal to 4, r was equal to 3. So it is also true that 4 minus 3 is 1. And so if I take 4 minus 3, I will get 1 factorial in the denominator. Same thing applied up here. N was equal to 3. R was equal to 3. Okay, wait a minute. So you can see how this is where we need this exception right here. Because in actuality, what we have is we have n up top. We have, well, wait, n minus r. 3 minus 3 is not 1 factorial. But 1 factorial is the same thing as 0 factorial by definition, and they're both equal to 1. So this is still n minus r, n factorial over n minus r factorial. If you wrote it in the exact way it should be written, it would be 3 factorial over 3 minus 3 factorial. We know that 0 factorial can't be 0 because we know that there are 6 ways that we could rearrange the letters of cat. And if we divide by 0, we have a problem, and you can see that without this extra definition here, things do indeed blow up. But this is 3 factorial over 0 factorial, which is the same thing as 3 factorial over 1, which is the same thing as 3 factorial over 1 factorial. So 0 factorial equals 1 saves the day. Now, the question we're trying to address here is, what do we do if there are just too many quantities to multiply? Well, what we do instead is we use this formula. And let's put this all together now. Suppose you want to count the number of ways our items can be chosen from n of them, and the following 2 principles apply. This is the same definition as we had at the top. Items that have already been selected cannot be selected again, and the order in which those items are selected is important. Then the number of permutations, and this is where we now have a formula for it, of selecting our items from n of them is given by, okay, now we're using this notation, p of n comma r. There are 2 things that this function needs, and it's n factorial over n minus r factorial. Now, graphing calculators do have a button for this, and that's why we're developing a formula, so that when there are large quantities, you don't have to multiply it out by hand. But you can do a search for your specific calculator type. We're going to use desmos.com/calculator. So let's show that, for example 1, where we had 3 letters, we wanted to figure out the number of ways that we could select those 3 letters and rearrange them. In example 2, we had 4 letters, but we only wanted to select 3 of them, see how many ways they could be arranged. In example 3, we have 8 letters, we want to select, or 8 candidates, we want to select 3 of them, where order matters. And let's just see that by simply accessing these functions, we could do all this work that we still had to do some manual computing for, but we could do it with the push of a button. So here I am in desmos.com/calculator, and it seems like all this can do is some graphing for us, but there's actually this little extended keyboard here, and if you click the keypad, click on functions, scroll down a ways until you get to, let's see, beyond calculus, we want the number theory segment, and you can see that there's a button called NPR and NCR. Right now we're using NPR, we're going to learn about this soon. So click on NPR, and this looks different than we have it written down, but basically we have to insert and separate by comma N and R. So in our first example, we had 3 letters, from them select 3, and we get an answer of 6. Much faster. Now you could also just type in NPR, and you see that it goes from italic to to regular typesetting, and here we had 4 letters, select 3 of them, we came up with 24. NPR, 8 candidates, select 3 of them, we came up with 336. And just to show, there they are, same answers, 6, 24, and 336, but with the push of a couple buttons, we end up with the same answers. Now, even though we have these shortcuts, it's still really important to reason through the problem and make sure that what we're actually needing to use is in fact a permutation. So not all is to be ignored here. Sometimes it still helps to build a little bit of a table just to see, oh, you know what, this is going to be a permutation. But then at some point, counting becomes much more reasonable in technology. For example, let me come up with another one. Let's say I have 100 candidates and 50 different positions. So if this is in line with what we were doing above, there's our N, there's our R. For the first position, we have 100 candidates, position 1. For position 2, we have 99 candidates. And then for position 3, we have 98 candidates. You can see there's 50 of them. So this is actually going to have to go down to person 50. Person 50, which, by the way, this is not going to be 50. This is going to be 51, because think about not counting at 99. You're not going 99, 98, 97, 96. You're going 100, 99, 98. And so that will get you down to 51. So that's a lot of multiplications to try to do in the calculator, but if I type in simply NPR 100, 50, well, first of all, it's an astronomically large number. It's 3.0685 times 10 to the 93rd. So this decimal place moves over 93 slots, and that is in fact how many different ways you could fill 50 different positions with 100 people.